Western Blotting Part 3, Transfer, Blotting, and Visualization.
To process the gel further for the detection and visualization of specific proteins and/or molecules, the proteins are transferred from the gel onto a more durable material that can be manipulated and blotted with antibodies of interest. Transferring is necessary to allow antibodies free access to proteins and because polyacrylamide gels are fragile and difficult to manipulate. The transfer method most commonly used in Western blotting is electroelution, where an electric field is applied to the gel to facilitate the migration of the proteins out of the gel and onto a piece of membrane. Transfer is accomplished by placing the polyacrylamide gel in direct contact with a membrane made of nitrocellulose or another non-reactive material that binds to proteins and submerging both in a buffer-filled chamber. The gel membrane sandwich is placed in such a way that the negative electrode is located closest to the gel, while the positive electrode is located closest to the membrane. When the electric field is applied to the chamber, proteins in the gel migrate from the negative end to the positive end of the chamber, moving out of the gel and into the membrane, to which they become tightly attached. In the next step, the membrane is probed with an antibody that recognizes the protein of interest, specific residues, or chemical modifications. The membranes used for Western blotting have a high affinity for proteins, including antibodies. Therefore, before antibodies are added to the membrane, it is important to minimize nonspecific antibody binding to the membrane. The membrane is incubated with a solution typically containing a blocking agent, such as dry milk or purified proteins, in a mild detergent. Proteins within the blocking agent will bind to the areas within the membrane that are not already occupied by bound proteins, preventing nonspecific binding of antibodies in subsequent steps. After blocking, the membrane is then incubated in a solution containing blocking solution and the primary antibody that specifically recognizes the protein of interest. Incubation is then followed by a series of washes with washing buffer under mild agitation. Washing buffer contains the same mild detergent used in the blocking solution, which helps remove nonspecifically bound primary antibody. After washing the membrane to remove unbound primary antibody, the membrane is incubated with a secondary antibody, which recognizes the type of primary antibody used. As with the primary antibody incubation, incubation with a secondary antibody is performed in the presence of blocking solution, followed by a series of washes. Secondary antibodies are bound to a reporter enzyme or a fluorophore, which allows for the visual detection of primary antibody binding to the protein or modification of interest. Secondary antibodies also amplify visual detection because multiple secondary antibodies can bind to a single primary antibody. The most commonly used secondary antibody type for Western blotting is conjugated to the enzyme horseradish peroxidase. Horseradish peroxidase catalyzes a reaction that produces light as a byproduct. The amount of light produced is directly proportional to the amount of horseradish peroxidase conjugated antibody bound. The light signal is a transient product and will only persist while the reaction is occurring. The most common way to record light output is using X-ray film. The X-ray film is placed directly on top of the membrane after the addition of the horseradish peroxidase substrate. Increased time exposure of the membrane to the film will yield stronger signals but also increased background. Researchers also probe for proteins whose levels are known to remain constant within the experimental treatment to ascertain that the total amount of protein in all samples is relatively similar. To do this, the researchers can run a separate gel or strip the existing membrane of any bound antibodies to reuse it. Stripping the membrane of bound antibodies is accomplished by incubating the membrane with stripping buffer containing SDS and beta-mercaptoethanol under high temperatures. In the lab, stripping cannot be done more than 2 or 3 times before you begin to also strip proteins bound to the membrane, resulting in loss of signal.